Hello and welcome. And in today's video, I wanted to discuss concavity slash convexity and its interpretations. So there's many definitions, or three. I mean, that's a lot, but three definitions that we're going to be covering today. In most calculus classes, you may be introduced to two or maybe three, but you will not see the proofs that they are all equivalent. But believe it or not, they are equivalent, okay? So we're going to discuss this in detail with all the proofs. If you want a more general video with just an introductory level calculus on concavity, this is not the video, this is more analysis. So, before we can discuss our secant line interpretation for concavity, we're going to need to express an arbitrary point x comma y on a line between x1 comma y1 and x2 comma y2 by parametrizing a line between the points. So we're going to want some sort of variable parameter, and we want that variable to be able to describe this point entirely, right? And it'll make a bit more sense when I talk about this. So first, we're going to let A and B be the points x1 comma y1 and x2 comma y2 respectively. And they're going to be points on a plane, right? And all I'm going to do is that I'm going to write xy here. So I have xy right here, and I have x1 comma y1, which is A and B here. And C is right here. And then we're going to draw all of these lines here. Um, so we have some triangles, triangle AFC, triangle AEB, triangle CDB, and triangle AB, I think. I don't know if I already said it. And we're going to notice that the triangles AFC, AEB, and CDB are similar, right? Because we have these parallel lines. Um, and if you don't believe me, you could take this time to, geometrically confirm. But yeah, they are similar. And from that, we're going to derive that FC over EB is equal to AF over AE. And all of that just means x minus x1 over x2 minus x1, which is the total distance, is y1 minus y over y1 minus y2 is equal to y minus y1 over y2 minus y1. I just right here flipped the sign, right? But it's the same thing because we're dividing by two negatives. And here we get an alpha. Note when I say A is going to be different later on than alpha. Alpha, I'm going to say alpha. So keep that in mind. It's the ratio FC to EB, right? It's saying this distance right here is how much of this distance. And for the Y, it happens to be the same exact ratio, okay? Alpha is 0 when x comma y is the same point as A, and alpha is 1 when x comma y is the same point as b. Okay, so alpha is the fraction of the total distance x1, or sorry, x minus x1, the total distance x2 minus x1 that x minus x1 represents, right, for x between x1 and x2. That's what alpha is. It's a fraction, it's a distance. So given any point x comma y on the secant line between a comma b, using equation 1, which I derived over here, we may represent the x comma and y coordinates of x comma y as the following. So we're going to take equation 1, we're going to multiply by alpha, and we're going to get this. X is x1 plus alpha times x2 minus x1. And if you don't believe me, we take x is equal to x1 plus the ratio alpha is, and x2 minus x1 here. That's what x is. Or alternatively, you may choose to express it as x is equal to x1 plus, expand the parentheses, and then move ax2 there on what that side. And then we'll just write 1 minus alpha x1. And similarly, the same exact argument for y. So we get y is equal to alpha y2 plus 1 minus alpha times x1. Sorry, y1, right? So what we're going to get here is the following two equations, right? It is equations 2. So keep that in mind. This is our x and this is our y. So what we've accomplished to do is express x comma y any point as simply the following: alpha x2 plus 1 minus alpha x1, comma alpha y2 plus 1 minus alpha y1. So instead of talking about x or y, we're going to be saying alpha is some number between 0 and 1, and that is our point x comma y, right? We can express it in terms of x1, x2, and some alpha. Now, since alpha is this ratio, and by multiplying by x2 minus x1, we get that. We get by subtracting 1 minus alpha, that's 1 minus this. And when we, hopefully you know how to subtract by fractions, right? X2 minus x1 minus, right? X plus x1 over x2 minus x1, and the x1's cancel out. So we get x2 minus x over x2 minus x1. And if you want to confirm this, that 1 minus alpha is x2 minus x over x2 minus x1. Notice x2 minus x happens to be this distance right here. So of course that's 1 minus alpha. That makes sense, right? Um, and here we get equation 3 now, that we get an equation for x2 minus x and x minus x1, okay? So now that we have those two, we can say the following. Specifically, given the graph of a function f with x1 and x2 in the domain and x1 less than x2, any point x comma y on the secant line between the points can be represented as alpha x2 plus 1 minus alpha x1, comma alpha f of x2, which is y2, plus 1 minus f of x2, right? And we know it's f of x1 and f of x2 specifically because because what was it? Y2 and Y1 lie on the graph of f. And we can parameterize that segment at x, right, as the y coordinate, right, at x is alpha f of x2 plus 1 minus alpha f of x1, equation 4. It's very important when we're comparing the output at a secant line. That is what our y value is. And now we can finally discuss the definitions of concavity. Number one is the strongest definition by far. Um, and this is the one that we mean when we say concavity, right? It's the secant line definition. Intuitively speaking, it makes sense, and it's easy to confirm, but rigorously and mathematically and analytically, it's a lot more difficult to establish. So we say f is concave up or convex over a comma b if and only if for any two x1 comma x2 in the interval with x1 less than x2, and for all alpha in 0 comma 1, right, we're parameterizing x comma y, which is what we're doing, right? And then x is of course between x1 comma x2, but we don't care about x. I'm just saying what x is. We can describe it using alpha. F of x should be less than or equal to y. Remember, y is the output of the secant line, and f of x is the output of f at x. We're just going to replace f of x with x's alpha x2 plus 1 minus alpha x1. And the output of the secant line by the equation up here, equation 4, is just that. So that's our definition. And it is just the opposites for the switch the inequality for b. And as well, you can have a strict inequality, right, which is strongly convex, or if you have the or equal to part, then it is just weakly convex, but that's fine. You don't need to specify that it's weakly convex. Now, geometrically, if we draw any secant line, it will be above the graph, or at least never below the graph. However, if it's concave down, then it will always be below the graph, never above. The second definition is the tangent line definition, and it just says that if f is concave up, then we say f is concave up if all the tangent lines lie below the graph, or concave down if all the tangent lines lie above the graph. Here, I don't have a graph, but you can sort of imagine here that if we draw any of the tangents, they're going to be below, and if we draw any of the tangents um, in the concave down, it's going to be above. And keep this in mind because if you do want, then you should know that later on, if you want to determine whether a linear approximation is an overestimation or an underestimation, you need to look at whether the tangent line is above or below, and it comes directly from this theorem that we're going to talk about. More formally, we say f is concave up in a comma b if and only if for any x naught in a comma b, the tangent line to f of x naught of x is less than or equal to f of x for some x between a comma b. Notice, remember the tangent line at f of x not evaluated at x is just if you remember f of x naught plus f prime of x naught times x minus x naught. But I'll show you that later. And for concave down, it just flips the inequality. Finally, the monotonicity of the derivative as well has to do with something. And for a differentiable function f over a comma b, again, also for 2, it has to be differentiable. That's why 1 is the strongest condition. But for a differentiable function f over a comma b, it's concave up if and only if f prime is increasing, or it's concave down if and only if f prime is decreasing. This is the one you'll see the most in calculus textbook in, like introductory calculus, calculus 1, calculus 2. Um, and this is the one that you're going to be using most of the time, but the first one is the strongest. So I'm going to rewrite all the equations we've used for parameterization and secant line. And here we have a pretty large theorem. It's going to take a bit to prove. All three definitions for concavity are equivalent for differentiable functions. Remember, we said the secant line is the strongest because it doesn't rely on the differentiability of the function. But if the function is differentiable, then they're all equivalent. And here's how I'm going to prove it. I'm going to prove 3 is equivalent to 1 and 3 is equivalent to 2. So it must follow that in reality, 1 is equivalent to 2 is equivalent to 3. So we're going to prove first that 3 implies 1, right? The forward direction. We're going to assume f prime is increasing, and we need to prove that for all x1 and x2 in a comma b with x1 less than x2, and for all alpha in 0 comma 1 and x in x1 comma x2, f of x is less than or equal to alpha times f of x2 plus 1 minus alpha f of x1. I'm not going to repeat it because it's written, but that was the last time. Since f is differentiable on a comma b and continuous on the closed interval, then the mean value theorem applies to f over these two intervals, okay? We're going to split the intervals into x1 comma x and x1 comma x2. Thus, there is a c1 and a c2 in x1 comma x and x comma x2, respectively. Um, Notice this is not x1, this is x comma x2, right? So we're splitting it to the left of x and to the right of x, and we can use the mean value theorem such that f prime of c1 is the following and f prime of c2 is the following. Now, since we know f prime is increasing, then we know f prime of c1 has to be less than or equal to f prime of c2. So we'll rewrite that inequality here. And note, we know x minus x1 is alpha, right? That's that ratio, times x2 minus x1, which is less than or equal to, and x2 minus x is 1 minus alpha times x2 minus x1. But notice we can now cancel out the x2 minus x1, and we're just left with alpha and 1 minus alpha. And cross multiplying, we get the following. Expanding the parentheses out and doing some algebra and moving everything to the other side and by isolating f of x, we get f of x is less than or equal to alpha times f of x2 plus 1 minus alpha f of x1, right? And the proof for concave down, which is f prime is decreasing, is similar. So we've proven, what have we proven? Well, we've proven now that if the derivative is increasing, then the secant lines must be above the graph, right? And that is the proof for 3 implies 1. For 3 implies 2, right? We're talking now about the monotonicity of the derivative implying the tangent lines. We're going to assume f prime is increasing, and we're going to prove that for all x naught in a comma b, the following holds. Now we're going to take two cases. Either our x value can be to the left of x naught or to the right of x naught. Since Now for the first case, since f prime is increasing, again, right? What theorem are we going to use? Well, we're going to use the first, all right, first we're going to use, I think, as you can guess, the mean value theorem, and then we're going to use the fact that f prime is increasing. So first, this part is the mean value theorem, right? Hopefully you could see that. And this part has to do with f prime is increasing, okay? So we're going to write f prime of c has to be equal to that, which is less than or equal to f prime of x naught. But we know x minus x naught is less than 0, right? Because we said x is less than x naught. So since we said this is true, we can just multiply by x minus x naught, and we're going to swap the sign, like the direction of the inequality, because we're multiplying by a negative number. And isolating f of x, we get f of x is greater than or equal to f of x naught plus f prime of x naught times x minus x naught. But remember, this is just the tangent line to the graph f at x naught evaluated at x. For the second case, we're going to use the mean value theorem again, and we're going to get to the same inequality, but this time, right, we're going to get that f prime of c is greater than or equal to f prime of x naught. So we can, and this time as well, we're going to get x minus x naught is greater than 0. So we're going to preserve the exact same direction as here, and doing the exact same algebraic steps, we get the same conclusion. We're not going to prove it for concave down because it's basically identical. Now, the proofs for the converse directions are less well known, right? And less proven in classes, but they are accessible. None of the proofs require some crazy, you know, finding that no one could have ever thought of, right? We're not solving the Riemann hypothesis or the Basel problem here, right? There's definitely doable. It's just for a standard calculus class, it's not talked about. So we're going to let x1 and x2 be in the closed interval with x1 less than x2 and some notation, because before we enter the next proofs, we're going to need some notation. We're going to find the slope of the secant line from x equals x1 to x equals x2 as lambda of x1 comma x2, right? Lambda of this is just going to be the slope of the secant line, which is the following. Okay, so whenever you see lambda, just think, oh, it's the slope of the secant line, and I know how to write it. So we're going to have to prove a lemma, and there's two parts. If f is concave up by definition 1, which is the standard definition of concavity, over the closed interval, and x1 and x2 and x3 are all in the interval, and x3 is between x1 and x2, then lambda of x1 comma x3 is less than lambda of x1 comma x2 is less than lambda of x3 comma x2. What this theorem, or sorry, lemma is saying is that if a function is concave up, then the slope of the secant line is least between x1 and x3, and then it increases between x1 and x2, and then it increases between x3 and x2. All right, and for 2, it's saying that if f is concave down, again, by definition 1, and the same exact conditions are met, then this time the signs are flipped, right? Lambda between x1 and x3 is greater than lambda between x1 and x2 is greater than lambda between x2 and x2. And the reason we're using lambda just for simplicity, right? Make our lives easier. And of course, you can confirm this geometrically, but we're going to prove it, okay? So assume f is concave up by definition 1, and we'll let x1 comma x2 comma x belong to the interval with x1 less than x2, right? So x is between x1 and x2. We're going to let alpha be between 0 and 1 such that x is equal to x1 x sub 1 plus alpha times x2 minus x1, right? Remember, this is the parametrization that we were talking about before for secant lines. We're just going to use that. And we have the following, which remember I already proved, but I'm going to re-show you why these things are true. Now, recalling this, right, which is our definition 1, we have lambda of x1 comma x, which is right as this definition here shows, which is just this because we're plugging in x with right x1 plus alpha times x2 minus x1. And remembering now what we're going to use this to our advantage. We're going to write less than y, right? And the reason why we're using less than is we're assuming a strict convexity, not the weak convexity, which has this or equal to. But if it was weak, then we could just write or equal to, right? So this, right, has to be less than this. And of course, if we're just subtracting, right, then it doesn't matter. The larger number minus the constant the lesser number minus the constant is less than the bigger number minus the constant, right? So hopefully that makes sense, right? And we were just writing this here, which is what we got from here, right? And now we're just going to do some algebra. In order to get this into a form we want, we're going to just do we're going to like right expand, we're going to cancel out f of x1, and we're just going to get alpha times f of x2 minus alpha times f of x1 over alpha times x2 minus x1, and factor in our alpha and canceling, we get f of x2 minus f of x1 over x2 minus x1. But this is lambda, which is the slope of the secant line of x1 comma x2. So we have proven the first one, right? Now, the second one is equally as easy and relies on the same exact idea, except this time, right, we're going to say that the other side is true because this time we're subtracting by a larger number, right? So subtracting by a lesser number is going to be greater, but the same exact idea. This time we're going to have 1 minus alpha cancel out. And when they do cancel out, we're going to have lambda of x1 comma x2. Since we have these two, we can combine them and get that it must follow that our lemma is true. You see the lemma right here? That's what we're saying, right? And we've proven it for concave up, but for concave down, it's similar, just flipped. Geometrically, we want to interpret what this lemma is saying. We're going to fix a point, right? And geometrically, it's saying that by sliding a point to the right, we're increasing the slope of the secant line for concave up. And if it's concave down, if we fix a point and we slide some point further to the right, the slope of the secant is decreasing. So maybe it may be apparent or it may not be that this is going to show up in our other proofs. And finally, the only thing we're going to need now is that we can show, I'm not going to show, but it can be shown that if locally at some point C, if f of x is less than g of x, right? Remember, locally meaning not including C, then the limit as x approaches C of f of x is less than or equal to the limit as x approaches C of g of x. Crucially, though, it's not strictly less than because there is a contradiction or sorry, there is a counterexample that I won't show, but there is definitely a counterexample. We can only follow this weak inequality. And now we prove the converse. 1 implies 3. We're going to assume f is differentiable and that the secant line definition holds. We're going to let x1 and let x be let x and x2 um, x1 and x2 be in that interval, right, with x1 less than x2. This time, though, remember, here's the thing. We're going to choose the delta such that x1 plus delta is less than x2 minus delta. And in reality, we have the arithmetic mean is between x1 plus delta and x2 minus delta. And remember, delta has to be chosen to be so small that this can be done, and it can be chosen, right? And we're going to let h be any number between 0 and delta, right? So we have for all h between 0 and delta, we have x1 is less than x1 plus h is less than the arithmetic mean, which implies that for all h between 0 and delta, we can now apply our lemma, meaning that we have all of these slopes of the secant lines have to be less than each other. This one compares the two endpoints, right? This one compares the first two, and this one compares the last two. Hopefully you could see that, right? This is our application of the lemma because f is concave up, okay? And that means that f prime of x1, right, which is the limit as h approaches 0 plus, because the limit does exist, right? F is differentiable, so the limit exists, and this is if it's not clear, this is the limit definition of the derivative. Although we're using lambda, this is just if you want to visualize it, f of x1 plus h minus f of x1 over x1 plus h minus x1, which is h, which is the derivative, the definition of the derivative, right? That is less than or equal to by this right here, that the limits have to be less than or equal to this lambda, right? And you may be thinking, shouldn't it be the limit? Yes, but it's a constant relative to the variable that we're using in the limit. So it's just that, right? The limit of a constant is just a constant. Similarly, for all h between 0 and delta, we have this being true, right? Obviously, we already said we chose h so that this is true. And since h is positive, this is true. We have that by applying our lemma. In this case, we have that lambda of x2 minus h and comma x2 is greater than, and this is lemma, by the way, right? This is our lemma. We're just flipping it in the opposite direction. So this is the greatest one. This is the second greatest one, and this is the smallest one, but we don't use that one. All right. So f prime of x2 is the limit, right? The same exact limit of the difference quotient, which is greater than or equal to this, okay? And we're going to use this. This is pretty crucial. This is greater than or equal to that. This is less than or equal to that. And just so a little note, we know the limits exist by the differentiability of f. So if f is not differentiable, we cannot do this step. Combining everything, right? We're going to result in the following. So first, we're going to use the lemma here, right? Since we're going to use the lemma here to get that lambda of x1 comma x1 plus x2 over 2 is less than lambda of x1 plus x2 over 2 comma x2. Hopefully it is apparent. You might want to convince yourself that this is an application of the lemma, but we know this is true and this is true. So it must follow that f prime of x1 is less than f prime of x2. But since x1 and x2 were arbitrary, f prime is increasing over the entire interval. And since now 3 implies 1 and 1 implies 3, we conclude they are equivalent for differentiable functions. And now we prove the equivalence of the tangent line definition and the secant line, right? So how are we going to do that? Well, we're going to get f, right? And by the way, we could have just proven another way, but I think it's more interesting, right, to prove that two is equivalent to 1. And from there, we can also get 3 is equivalent to 2. But I wanted to show you as many proofs as possible, so you don't have to prove, right? Like everything here, I don't believe. I think I added one more proof that wasn't necessary to establish the equivalence. Nonetheless, I think understanding all the proofs can be pretty helpful. Um, but the important part is that we did prove it. Given f, we're going to define this. This is just a notational choice. G x bar, I'm going to call it bar x naught, as the following. It's the difference, right? If we can look at it here. G of x bar x naught measures the difference between f and the tangent line of at x naught of x. So when g of x bar x naught is positive, the function is above the tangent line, and when it's negative, it's below. You might want to, show that this is true, but this is true, right? We know the tangent line definition. If we can establish g is positive, then it's above, and if we can establish g is negative, it's below. Now we're gonna prove 2 implies 3, okay? Um, this is the key step here, okay? And this is actually where what's it called? Uh, we didn't I didn't overprove anything, right? We're going to finish our proof. We're going to conclude, right, that this is all true, right? And we don't actually prove 2 is equivalent to 1, by the way. We prove that with the fact that equivalence is transitive, but we're going to prove that 2 and 3 are equivalent, and then we can prove 2 and 1 are equivalent. So assume that for all x and x naught in the interval, which x naught being equal to x naught implies, right, that g is positive, okay? And this is the same thing as saying f is above the tangent line, strictly above, as long as x is not equal to x naught. And we'll let x1 and x2 be in the interval, right, with x1 less than x2. So what do we have? We're going to first compute g of x1 bar x2, which we know is positive, right, given, which is f of x1 minus the whole, f prime of x2 times x1 minus x2 plus f of x2. That's positive. So f prime of x2 times x1 minus x2 is less than f of x1 minus f of x2. And by flipping x1 and x2, we get this result, okay? So if we divide by this here and we divide by this here, what do we get? We get that f prime, right? If you want to look, f prime of x1 minus f prime of x2 times x2 minus x1 is equal to f prime of x2 minus x1 plus f prime of x2 times x1 minus x2, and that is less than this, right? But what is this actually, right? Because what we're doing is, um, I don't know if it was apparent or not, but we're adding these two inequalities, right? Um, yeah, so what we're doing is we're adding these two inequalities. We're factoring out x2 minus x1. Of course, in this case, we're gonna take like a negative sign here, but we're adding the two, right? We're gonna get this. Actually, you could say we're subtracting it. That's fine, but we're not. We're adding it. And what we're gonna get is this, right? But that's less than this, which is 0. So f prime of x1 is minus f prime of x2 is less than 0 because x2 minus x1 is positive, right? Right. This is positive, and this is less, and this whole thing is less than 0. So this has to be negative, right? So we have shown that for all x1 and x2 in the interval, x1 being less than x2 implies f prime of x1 is less than f prime of x2. And that concludes all our proofs, right? We've proven 3 implies 2 and 3 implies 1 and 1 implies 3 and 2 implies 3. So 3 is equivalent to 2, 3 is equivalent to 1, so 1 is equivalent to 2. So all of them are equivalent for differentiable functions. And hopefully this gave you some insight into analysis and studying convexity, right? This isn't typically taught in like a first year calculus course, which is why it's a bit more complicated, but the concept is definitely accessible, right? And hopefully this made sense. And if you do have any questions, because this may be a bit hard to digest, if you are left with any questions, feel free to comment them and I will try to answer them to the best of my ability. So, good luck and keep studying,